In my opinion, examples are the best way to show things and the best way to learn new stuff. So regardless if you have watched the previous videos, the only thing you need to know is how to install NODEMaple, which I've shown you in the first video. But now I think we should dig right into the example sections, and our first example is the ultimate limit state. And before that, you need to know how to download the examples. So let's just have a check. The first thing is you need to go to NODEMaple on GitHub again, and you see you have downloaded the packages probably already. The NODEMaple includes the maple files, and the source code includes the example. So if you download this part, I've already done that, you're doing the unzip, and within this folder you will see the example section. It's the ultimate limit state example is here. So from now on we're going to have a look at both the ultimate limit states and the fastness example. So let's just open NODEMaple, and that's the example we're going to have a look at. Everything here is in Norwegian, but there are a couple of illustrations, so you might have a look at them as well. There's one thing with the Limtreboka examples, and I'm going to post a link in the description of this video, is that the layout of the book is quite strange. So you have not a continuous reading like it would be in a book, but you always have a left side and a right hand side. So the best way to look the PDF is to switch on the 2 pages layout, and we're going to have a look at the left hand side while the calculations are on the right hand side always. So the illustrations left hand side and the explanations as well, while the calculations and the text is on the right hand side. It is a simple glulam beam with a span of 7.5 meters. We have a live load and we have a self-weight on the system as well. The influence length of the load is 4 meters, and you can expect to be a floor which is helping against the buckling and the weak axis. Glulam qualities GL30C. The climate class is 1, and so which means is inside of the building. And we are going to have a look at the rest afterwards, but let's just check it. On the left hand side the explanations, on the right hand side the calculations. So let's just open the Maple sheet. We have opened NODEMaple, and as it is an ultimate limit state example, you need to open the sheet number 6, or the chapter 6 of the Unicode, which is the ultimate limit state. Next thing is to import the XML file. Go to NODEMaple, Timber, ULS, and open the example number 1. This does read in the XML file and maps the input data to the sheet. So we have this explanation. This is not in the XML file, but this is in the sheet itself. So we have section 6 for ultimate limit state design. The project number is defined by myself, and we have these Norwegian text for the Limtreboka, which is the glulam book calculation example. The client, this could be yourself. I have just taken the company which I'm working on. Position number and the text of the example. The system is, as I've said, a glulam with a width of 140 millimeters and a height of 585. This one is just the pull down menus, so if you are going to open the XML file, it might be different here. That's not the one that is used for calculation, but the text within the green boxes is used for the calculations. So we have a strength class of GL30C, service class 1, and the load duration class is a medium term, which gives a key mode of 0.8 and a gamma M of 115. These are Norwegian safety factors, so your country codes might have different ones. So the next thing is the buckling and lateral torsional buckling length, which we're defining here. The LKY is the buckling length around the y-axis, which is the strong axis. And the LKZ is the buckling length around the weak axis, in direction of the weak axis. As we have the floor in the weak axis, so we can put this value quite low. So let's just assume it as 1 meter, while in the other direction is 7.5. LEFY is the effective length regarding lateral torsional buckling. And here the Limtreboka gives us some information. Let's just see what we have got here. For a load on the top side of the beam, in addition of the length, you also need to take account for twice the height of the beam. So in that case, the buckling length is 7,920 millimeters. So let's assume here we take in the 8 meters here. On the across the weak axis, it's not so necessary to define because we don't have any bending moment in the weak axis. It's just along the strong axis. So let's just continue with the input. We do also need to check the continuous and discrete supports, which means that we need to check this part of the system. So we need to check the compression perpendicular to the grain. So the effective length is going to be calculated by the program, while the column of this system needs to be we need to input the column width of the beam, which is 140 of the column, which is 140 millimeters. I'm sorry, 140 millimeters is the width, while the length of the column, or the height, is 225 millimeters. So in that case, we need to enter the 225 millimeters. We have a distance to the edge of the beam, which is 0. And we have a distance between the supports, which is 7.5 meters, 7,500. Compression at an angle to the beam is in that case not relevant, so it won't be calculated. We don't have a varying cross-section or curved shape either, so just check that this one is not defined. And we don't have an end notch beam either, so just check that the end notch is switched off. Regarding the loads, we do have 3 different kinds of loads. We have the moment, the shear, and the support. The support is a compression perpendicular to the beam. So the moment, all these values you need to calculate by yourself, or you get it from a table, or you get it from a calculation program like a finite element or a usual structural beam design software or something like that. So in that case, we have the moment already, which is 142 kilonewton meters. We have the shear, which is 76 kilonewtons, and in that case also the force perpendicular to the grain is the same. So we have the moment, which is 142. We have the shear, which is 76 kilonewtons, and we have the compression perpendicular to the grain. In that case, you need to enter 76 with a minus, and you also need to set the alpha, the direction of the force, to 90 degrees. So that means that the structure is going to be put on a 90 degrees force perpendicular to the grain in that case. There are a lot of information in this part of the sheet. So let's continue. The material and section properties are just for information, so there's nothing to input, but you can check your own values with these values here in this table. So let's go on for the calculation. We have an automatic calculation in that case, and it also is possible to calculate all load cases. So we have 3 different load cases which are acting upon the construction, and pressing this button will update this value down here. So in that case, the worst of the 3 is the load case moment, which gives a value of 0.98, which is still okay. But right now we are calculating the support, because I have not done a reset to the value, so we're going back to the moment if you're going one by another. And in that case 0.98 is the same as this one. The calculation which is done is according to 0.6.3 in the Eurocode, or more specific 6.3.3 with formula 6.33. The text is beams subjected to either bending or combined bending and compression. And the values which are necessary to check the calculation are here in the result details. So we have in KH 1.0, KHP 1.10. The other values here are not relevant, they are just grayed out. So we're going further on to the stability of members, and here you have the necessary values you can use for check your personal calculation if you wanted to do that. So everything here is listed, the eta values for each of these calculations, and in that case eta 6.1.6 and 6.3.3 are the highest values. So 6.1.6 is the one which gives you 0.98. So let's just continue and have a look at the shear. 76 kilonewtons. We have these two are calculated as well, and we have the shear width not just as support. KCR is 0.8, KN 6.5, and the other values are here. So the check is 0.71 for the shear. And the last one is the support check. Compression perpendicular to the grain, the Euronorm, which is the Eurocode. Here there is something specific to Norway. In Norway we also have we have two methods of calculating the eta values here. We have the one which is the standard Eurocode, but we also have a possibility to do a calculation according to an NTI calculation report, which opens up for a different kind of calculation. We are going to calculate both of them here, but the least of the values is taken into account. So this one is actually the Eurocode, which gives the lowest result, and this one is used here as well. So having finished the example, you just can go through the example once again, and you can check everything if it's according to the calculation. So this was a very quick overview of how our calculations are done in the example sections, and as I've said in the start, I'm going to post the links for the Limtreboka, and see you in the next example.